Good morning to everyone and welcome again to the AMP conference. Before we start, let me mention that in the general chat, you will find a link to the talk of Professor Dereziński. And then, so the first talk is by Jan Dereziński from the University of Warsaw. The title is The Feynman Propagator and Curved Spacetimes. Please begin, Jan.
Yeah, I would like to thank the organizers and especially Ricardo for organizing this meeting and for inviting me and for selecting this subject for my talk, because I also proposed some other less challenging topics. This will be about the Feynman propagator and other propagators which are used in quantum field theory. And this will be based on my work with collaboration of Christian Gass. Let me start with a short introduction. I will discuss curved spacetimes and various natural green functions and B solutions of the Klein-Gordon equation. There is a whole zoo of propagators or two-point functions which are useful in quantum field theory, which one can define, which are usually defined on the Minkowski space, but it is interesting to generalize them to a more general setting, that of curved Lorentzian manifolds. They are key ingredients in perturbative quantum field theory. I mean, maybe some of you are asking why I'm talking about this in this conference, but as you will see, there is a lot of operator theory involved in this subject, and in my opinion, a beautiful operator theory. Let me start with the flat Minkowski space. This will be something which is standard knowledge for students of quantum field theory. At least it used to be. I will first describe what we would like to generalize to a curved setting. I don't know how many of you took a course on quantum field theory, but this, in principle, this should belong to education of a physicist or a mathematical physicist, and indeed, this is a difficult subject, and actually the way it was taught changed over the times. So many things which were taught in the old days are not even mentioned nowadays, or only marginally. One of the tools of quantum field theory are the so-called green functions of the Klein-Gordon equation. So a green function is how do you so this is the Klein-Gordon equation, and a green function is a distribution which depends on two parameters, space-time positions x and y, and when you act on it with the Klein-Gordon operator, you get the delta function in both variables. We will also need B solutions. So again, a function of two variables, and when you act with the Klein-Gordon operator, you get 0. So that's so the green function is essentially something like an inverse. However, an inverse of the Klein-Gordon operator. However, the Klein-Gordon operator is not invertible, so it's not a strict inverse, and you may have many green functions. Now, there are 4 green functions which are invariant with respect to the restricted Poincare group, and I am giving their definitions in terms of their Fourier transforms. So essentially, you invert p squared plus m squared, and then you have to prescribe the way you bypass the singularities. And there are 4 ways to do this. So this is, if you this is kind of a standard textbook material from the old textbooks. Now, this way you define the so-called forward and backward propagator, also called the retarded or advanced propagator. I mean, in this subject, there are many names. Many objects have many synonymous names. So the forward and backward propagator, which I will denote like this, they are related to the classical Cauchy problem. They are supported in the forward and respectively the backward light cone. Besides, there is the Feynman and anti-Feynman propagator, and this will be actually more interesting for me. they are also inverses of the Klein-Gordon equation. However, they are not, their support is not causal, and they are relevant for quantum field theory, not so much for classical field theory. And let me mention the following identity, which I mean is obvious if you look at the definitions here, and this identity will play an interesting role later on, and we'll ask when whether it is satisfied in on curved spacetimes. And so now, if you take the difference of two green functions, you get AB solutions. And here I'm listing three of them which play an important role in quantum field theory. One of them is sometimes called the commutator function. There is also a name Pauli-Jordan function or Pauli-Jordan propagator. So it is the difference of the retarded and advanced propagator. It has a causal support, so it is supported both in the forward and backward light cone. Besides, there is the so-called positive frequency or Weidmann two-point function. We will see that this is a two-point function of a quantum state. There is also a negative frequency two-point function, which is closely related. Jointly, all these green functions and B solutions will be informally called propagators. I mean, the word propagator does not have a fixed meaning, so it's the terminology is quite messy, and it is a short, nice word. So we will use it as a joint name for these objects. Now, I will not discuss the quantization. I will just assume that I mean it's actually a natural. It's a sort of a functor. By quantization, you obtain an operator value distribution which satisfies the Klein-Gordon equation. So that's so as you see in notation, I put hat on psi to indicate that it is the quantized object. Now, the commutator of these fields is given by the Pauli-Jordan function. So this is the reason why it is also called a commutator function. Now, after quantization, we get a representation of these fields in a Fock space with Fock vacuum. So omega is a Fock vacuum. And you can compute expectation values of the fields. So here you have psi star or psi star psi, and there is an easy computation which shows that they are given by the positive frequency and negative frequency B solutions. It is obvious that they are B solutions since psi hat solves the Klein-Gordon equation. Now, what is also useful in quantum field theory are time-ordered products of fields, and if you compute them, you get the Feynman propagator, and if you compute the anti-time ordered product, you get the anti-Feynman propagator. So this slide shows you the the physical meaning of these propagators. Now, as I promised to you, the talk will be to a large extent about operator theoretic interpretations of these propagators, and there are two of them. The first is the following. So consider the Hilbert space of square integrable functions on the space-time, on the Minkowski space-time. Now, it is easy to see that the Klein-Gordon operator is essentially self-adjoint on compactly supported smooth functions in the sense of this Hilbert space. And the Feynman propagator turns out to be the boundary value of the resolvent of the Klein-Gordon operator in the sense of some limiting absorption principle. So, the Feynman propagator is the boundary value from above, and anti-Feynman propagator the boundary value from below. There is another theoretic operator theoretic approach to Feynman propagators, which I will discuss now. But before I do this, let me remind you that you can get the slides for my talk from my web page, and Ricardo sent the link to so I mean that I know that the talk involves many concepts, and so maybe it is helpful to have these slides on your computer. And please interrupt me with questions if something is not clear. So the second the second operator theoretic approach is based on Cauchy data. So Cauchy data for the Klein-Gordon equation involves the value of a function on a certain Cauchy surface and its time derivative. And so it is the direct sum of two Sobolev spaces with appropriately chosen exponents. Now, this space has a natural Hilbert space structure, but more importantly, it has also an indefinite scalar product, which is sometimes called the Klein-Gordon charge form. So, which is its definition is given here. So as you see, W1 is paired with V2. So this is definitely not positive definite. Actually, this charge form is more important than the positive scalar product, and this space should be understood as a Klein space. So the Klein space, as you probably know, is a space with the topology of a Hilbert space and a distinguished Hermitian form, which satisfies certain property. And now, what is this property? That there exists a linear operator, an involution, which I denote as bullet. I mean, bullet indicates that there may be many such involutions. Now, so involution means that S squared is 1, And if you put this S inside the charge form, you get a scalar product which is compatible with the topology of our space. Now, how do you obtain this charge form? There is a natural conserved current on the space. So if you have two functions which solve the Klein-Gordon equation, so W is the space of solutions of Klein-Gordon equation, then this quantity is conserved, which means that its divergence is zero. So if you integrate it over an arbitrary Cauchy surface, you get a quantity which does not depend on this surface. So you can integrate it over a constant time surface. And this gives you the Klein-Gordon product, which I already mentioned. Now there is a concept of the suppose you what is the importance of B solutions? Suppose you have a B solution of the Klein-Gordon equation, then you can pair it with any element of this Klein space using this Klein-Gordon product, and then you get a linear operator, and the linear operator on this Klein space. You obtain a linear operator, and one can call this B solution the Klein-Gordon kernel of this operator. For instance, the Pauli-Jordan B solution is the Klein-Gordon kernel of identity. I mean, this is probably not obvious, but this is actually an interesting fact about the Pauli-Jordan function. Now, the Klein-Gordon equation can be rewritten as a first-order evolution equation preserving the scalar product, and even more importantly, preserving the charge form. So here I wrote this first-order differential equation. Since the Cauchy data is the direct sum of two spaces, then this operator is a 2x2 matrix like this. Now, if you introduce the projections onto positive and negative spectral subspaces of this generator of the evolution, then you get some projections on this Klein space, and then it is not difficult to check that these positive and negative frequency B solutions are the Klein-Gordon kernels of these projections, actually with the sign plus or minus. Now, this is the end of the first section of my talk, where I discussed the flat Minkowski space. This was a kind of resume of the standard free scalar quantum field theory. Please, this is a good moment to ask questions. Ricardo.
Well, at this, I don't know if anyone has a question.
The idea is that this was kind of a standard knowledge, maybe explained in a different way than it is usually done in textbooks. But I mean, that should be known to people who studied elements of quantum field theory. So please, this is the right moment to complain if this was not clear.
Well, just a question. I guess you use the metric time with plus and space with minus, right?
Actually, I use time with minus and
Time with
space.
minus, okay.
Yes, that's yeah, and there is actually a reason. I like to do the Wick rotation, and it is easier to do this in that setting.
If time has a minus sign.
Yeah. Okay, so let me continue. So now it will be, I mean, we will consider a curve space-time. Now, let me stress that I am not discussing the theory of gravitation, general relativity. This is about quantum field theory. So I don't care whether the curved spacetime is a solution of the Einstein equation. This is completely irrelevant. I mean, but the point is that quantum field theory is naturally generalized to a curved setting, provided that the curved spacetime is not very pathological. So the usual flat D'Alembertian is replaced by the following operator, where G mu nu is the metric, and then you add mass squared, or actually you can add a potential, a scalar potential, which depends on the position and time. We will restrict ourselves to globally hyperbolic spacetimes. So globally hyperbolic means that it is a Lorentzian manifold possessing a Cauchy surface, and time flows forever. So, I mean, there are several rigorous definitions, but let me just skip them. Now, it is well known that if the spacetime is globally hyperbolic, then one can define it is clear how to define the forward and backward propagator. So this is a unique green function with the support which is in the future or the past region of a given point. So that's this is a classical fact which goes back to Hadamard, Leray, and it is well known in the mathematical literature. Now, what about the finite propagator? This is less obvious. Now, let me propose one possible generalization of the Feynman propagator. It is clear that the D'Alembertian is Hermitian, is symmetric on the space of compactly supported smooth functions on the manifold, in the sense of the Hilbert space of all functions on this on spacetime. Now, assume that it is essentially self-adjoint, which is well, one should expect that it is. Now, you can try to look at the resolvent of this D'Alembertian so the of the minus D'Alembertian plus m squared, and one can ask whether there exist limits from above or from below on the spectrum. And if they do exist, then you define the so-called operator theoretic Feynman and anti-Feynman propagator as the limits of the resolvent. Now, why this is a reasonable definition? Now, first let me mention the following fact about Fresnel integral. So Fresnel integral is an integral of the, it's similar to Gaussian integrals, except that you have I in the exponent. So this is an identity which you can easily check. So here C is a number, or actually it can be a real matrix, and you need to add plus or minus I0 to this matrix, to the inverse of this matrix, to compute these quantities. Now, this plus and I0 is very similar to what you see here. Now, if we use path integrals, and the path integrals is the favorite method of physicists for quantum field theory, and if you assume that the action is quadratic, so what does it mean quadratic? It means that it is a quadratic form in fields, and the form is given by the D'Alembertian plus m squared. Well, of course, mathematicians say that path integrals are ill-defined, that this is non-rigorous, etc. But for quadratic Lagrangians, the mathematicians are wrong. I mean, this is well defined if you adopt this definition, and here you see the Feynman propagator. Now, what about the self-adjointness of the D'Alembertian? It is sometimes easy to prove. So, for instance, for stationary spacetimes, for the so-called Friedmann-Lemaitre Robertson-Walker spacetimes, this I will mention. I explain this later. For one-dimensional spacetimes, I mean, this may sound funny, but this is actually an interesting point. And for spacetimes with a lot of symmetry, for instance, de Sitter and anti-de Sitter spacetimes, the D'Alembertian is essentially self-adjoint. Now, for generic spacetimes, this is actually a difficult problem to prove self-adjointness, and this was considered and proved in some special cases only quite recently. So there are proofs by Vasi and by Nakamura Taira who considered asymptotically Minkowskian spacetime, so a rather restricted class of spacetimes, but kind of generic. So this was the first attempt to generalize the operator theoretic setting. Now the second attempt. Which is let's consider the quantized. Let's first describe this in a quantized setting, like physicists usually do. So how do you introduce quantum field theory on a curved spacetime? First, you assume that you have a field. Field means an operator value distribution, and its commutator is given by the Pauli-Jordan function. I mean, Pauli-Jordan function is well defined on globally hyperbolic spacetimes. Then one needs to select a Fock representation. This was quite easy in the flat setting because you had a lot of symmetries. Now, in the generic setting, it is not so obvious, but suppose you somehow you selected Fock representation, so you have a Fock vacuum, which I call omega sub alpha. Alpha indicates that there may be many various Fock representations. Then you have the 2-point functions. I mean the positive frequency, the negative frequency. You have also the Feynman propagator, which involves time ordered products, and the anti-Feynman propagator, which involves anti-time ordered products. This identity, which I mentioned, is still true. Now, Hadamard condition, let me skip this for now, but now, what is not so well known, but it actually will be important in what follows, is that you can also consider a pair of vacua. So one I call omega alpha, the other omega beta, and then one could consider mixed 2-point functions and mixed Feynman propagator. Now, it turns out that one should, so there is the expectation value, but then one should divide by the overlap between these two vacua. Now, one can protest that this, okay, that now, let me just mention easy facts. If this is well defined, then these two objects are still B solutions, and these two are still green functions. And they are useful in quantum field theory. This is easy to imagine. And they satisfy various identities which are listed here. Now, if you see that there is a denominator here, then you should probably protest that this could be 0. In reality, it often is 0. So what is the meaning of that? Now, if you use operator theoretic approach based on an appropriate Klein space, then there is no issue. So then you can define this rigorously in great generality without worrying about dividing by 0. So I mean, I will not describe in detail this setting, but you can imagine if you know the Minkowski space and its Klein space of Cauchy data, then you can easily generalize this to this the curve setting. Now, suppose that the Klein-Gordon equation is stationary. Stationary means it does not depend on time. So the and another assumption, suppose it is stable. Stability means that the classical Hamiltonian is positive or non-negative. So in practice, it means that mass squared is non-negative, because one can also consider mass squared which is less than 0, and this is the so-called tachyonic case, but we don't want tachyons. Then one could repeat the construction from the Minkowski space. There is a unique distinguished vacuum omega given by positive frequency modes. It is defined very similarly as in the usual case of the Minkowski space. And then the operator theoretic Feynman propagator coincides with the time-ordered, with the expectation value of the time-ordered product of fields. So everything is as it should be. So the two definitions of the Feynman propagator agree. Now let us be more general. Suppose that you have an asymptotically stationary and space-time. So asymptotically means in far future and in the far past. And it is not only asymptotically stationary but stable. So in the far future, the mass is positive, the mass squared is positive, and in the past as well. Then you can define two natural states: the in vacuum and the out vacuum. So the just following the usual approach in the stationary case. So you can introduce the out-in Feynman propagator. So here you have the out states, here you have the in state. You divide by the overlap. So again, if you worry about division by zero, you just use the operator theoretic approach, and this gives you the definition. Now, what is this is a very natural object, because if you want to compute the scattering matrix, which is what physicists want to do in quantum field theory, then these Feynman propagators will be associated with the lines of Feynman diagrams. So when you have a Feynman rules, then with every line you put the Feynman propagator. So this is essentially the content of the Wick theorem. Now it turns out, and this is not a trivial fact, that this is well defined. That this is if you have an asymptotically stationary stable space-time, this is a well-defined object using this operator theoretic approach. Now, one can heuristically derive, and under some technical assumptions even prove rigorously, that these Feynman propagators, this out-in Feynman propagator, is the same as the operator theoretic propagator. So again, the two definitions agree, and similarly for the anti-Feynman propagator. So that's now. Okay, again, I invite questions. So
any questions? Well, I have some, but I do not want to interrupt you. Now, with this propagator satisfy the Hadamard condition?
Yeah, well, the Hadamard condition is not about Feynman propagator. It is about a two-point function.
Yes, about the two-point function. Sorry.
Yes. So the two-point function. So here you have the in vacuum and the out vacuum.
Right.
They satisfy the Hadamard condition. And this is not a trivial fact, and this was proven by Gerard and Wrochna. So the answer is yes.
And then how, well, maybe this will take you far beyond, but how do you characterize the Hadamard condition in this general setting? By some microvocal analysis?
Yeah, I mean, okay, I wanted to avoid discussing the Hadamard condition. It's so in a few words, Hadamard condition is the condition that says that two-point function is similar to the Minkowski two-point function. And these in vacuum and omega and out vacuum, they are such. So the formalism gives you for free the Hadamardness. Now the definition is the same. I mean, it is the one that you know.
Oh, okay. Well, thank you.
But sort of, I actually. I think that there is too much emphasis on the Hadamard condition here. I mean, I'm discussing quantum field theory almost without mentioning this.
Okay.
Now, suppose that the space-time is globally hyperbolic and the D'Alembertian is essentially self-adjoint. Now, let me introduce the following funny definition. We will say that the Klein-Gordon operator is special if the support of the sum of the Feynman and anti-Feynman propagator is contained in the causal shadow of, so if you fix a point y, then it is in the causal shadow of y. So I mean, the Feynman propagator is alone is not does not have a causal support, but maybe when you take the sum, it is. If this is the case, then by splitting this distribution, you can we expect that I mean, you can split this distribution into a part in the future shadow and in the past shadow, and one of them will be the forward propagator and the other will be the backward propagator. So if you have a special Klein-Gordon equation, it is quite nice, because then from the Feynman propagator and anti-Feynman, you can compute the forward and backward propagator by multiplying with the theta function. And then you can also compute a distinguished two-point function, a two-point function of a distinguished state. So this it is very nice. Now, unfortunately, this does not work on generic spacetimes. It works only if the in state is equal to the out state, and then this is okay. So it works if you have a stationary spacetime, which is already quite something. Now, say stationary and stable. Now, it turns out that sometimes on non-stationary spacetimes, that property, this specialty property, which I recall, it's defined here, is also satisfied, and maybe I will tell something about this. So this was the end of part 2, so of the general part. And now I would like to discuss examples. And I think I still have a little time. So stationary, I already discussed. Tachyonic, they are not special. I mean, but you can define you can define the Feynman, anti-Feynman, forward and backward propagator also if m squared is negative. You don't have distinguished states then, but it's not very physical, but okay. 1 plus 0 dimensional spacetime. So when you have only time and no space, then the Klein-Gordon operator is essentially the one-dimensional Schrödinger operator, about which, essentially all participants of this conference know everything. And then it turns out that this one-dimensional Klein-Gordon operator is special if and only if this one-dimensional Schrödinger operator is reflectionless at energy m². Now, as you probably know, there are non-trivial potentials which are reflectionless. So reflectionless means that the S matrix is trivial. And the main example is the inverse Cauchy squared potential, but for special values of the coupling constant. So alpha has to be a half integer. And we will see an application of this. Okay, now a big example. So far these were easy examples. Well, not easy, but now let me discuss the de Sitter space. So consider the D+1 dimensional Minkowski ambient space, and in this ambient space we introduce the so-called one-sheeted hyperboloid, which is also called the de Sitter space. It is a Lorentzian manifold, and let's look for the Feynman propagator by solving the usual equation. In fact, this is a maximally symmetric space, and there is a mathematical theorem that the D'Alembertian, which says that a D'Alembertian on a maximally symmetric space is essentially self-adjoint. That's so we are sure that we will get we can compute the resolvent of the D'Alembertian, and it turns out that you have to solve the so-called Gegenbauer equation, and you find I have a picture. So this is the picture of the de Sitter space. If you select a point, then there is an antipodal point. So there is I mean, de Sitter space is quite tricky. But okay, I think I don't have time now for this. So so let's try to find a solution of this equation, demanding that the singularities of this Feynman propagator are similar to those in the Minkowski space. Then one gets a unique solution. So S here denotes a certain special function, a certain kind of Gegenbauer function, which is regular at 1. And W, you probably don't remember what is W. W is, where is it written? It is not written, no, it is written here. W is the scalar product of the 2 points in the ambient space. So this is the Minkowskian scalar product in the ambient space. This is an invariant quantity for a pair of points. You get a certain Feynman propagator, which is usually called the Euclidean Feynman propagator. I mean, I don't want to discuss why it is called Euclidean. These are strange names. I mean, the reason is that it is obtained by the Wick rotation from the Euclidean sphere. And it is the unique de Sitter invariant Hadamard state. And you have the specialty condition here, so you can derive the forward and backward propagator from this Euclidean Feynman propagator. Now, so I actually cheated a little. We were solving this equation, which looks like the equation for the resolvent, but this Euclidean Feynman propagator is not the integral kernel of the resolvent. You can compute the resolvent that's given by a different Gegenbauer function, and it turns out that the operator theoretic Feynman propagator is different from the Euclidean Feynman propagator. At first, this was quite surprising to us, but it's like that. The Sitter space is so pathological that I mean, the two objects which for nice spacetimes are the same are distinct here. And in particular, the Euclidean state is neither the in state nor the out state. Actually, there is a whole family of de Sitter invariant states parameterized by a complex parameter which can be called alpha. These states are sometimes called alpha vacua. And among these alpha vacua, there is the Euclidean state, and there is also something which can be called the in state and an out state. That's, well, strictly speaking, the Sitter space is not asymptotically stationary, neither in the past nor in the future. It explodes exponentially. So, but one can define in state and out state, and it turns out. So here you can compute the out-in Feynman propagator. Here is there is a formula. Actually, there are two formulas because they are different for odd dimension and even dimensions. You see Gegenbauer functions, but different Gegenbauer functions. It turns out that in odd dimensions, the de Sitter space is special, and the out and in vacua coincide. In even dimensions, this is not the case. There is an alternative approach to the de Sitter space based on global coordinates. So you can describe the de Sitter space by these coordinates. Then by choosing a mode decomposition, essentially by expanding in some spherical harmonics, you can reduce yourself to the one-dimensional Schrödinger equation, and this Schrödinger equation is precisely this scarf Hamiltonian with 1 over Cauchy squared potential, which I already discussed. And in odd dimensions, you have the parameter here. I mean, well, actually, there is not only a parameter, but there is also the Laplace-Beltrami operator on the sphere. And it turns out that then you get the reflectionless Hamiltonian. So you see, now you understand why the in state is the same as the out state. In even dimensions, I mean, this is still true, but you get the parameter, an integer for which this Hamiltonian is not reflectionless, and the in state is different from the out state. So that's this is the story about the de Sitter space, which is, I mean, we were really amazed how rich it is. Now, do I still have? I still have three minutes. So another interesting example is the anti-de Sitter space. The anti-de Sitter space is defined as a certain hyperboloid in the space with the signature two minuses, and the rest are pluses. Now, this is not very physical because the time goes in loops. Time is cyclic. But this is not very serious, because you can take its universal coverings, and then time flows from minus to plus infinity, and so you can imagine that it could be used for physics. But there is another problem. You have at space like infinity, you have a time-like boundary to which the geodesics go in finite time. So it is not globally hyperbolic. But it turns out that this is not a very serious problem. So here there are pictures. You should look at this picture, because this is this universal cover, and it shows the space-like and time. I mean, time-like regions. There is a kind of a sequence of an infinite sequence of regions, and one can apply again, one can apply the two methods that I discussed, the two operator theoretic methods. One is based on the self-adjointness of the D'Alembertian, and it gives you the Feynman propagator in terms of one of Gegenbauer functions. You can also apply the method of the evolution of the Cauchy data. And now this evolution is closely related to what is called the trigonometric Peschel-Teller Hamiltonian. Some of you like this Hamiltonian very much. So this is again exactly solvable in terms of hypergeometric functions, and so you can again analyze this in two ways, and these two ways agree. And I think I don't have more time for my talk, so let me stop here and thank you for your attention.
Many thanks, Jan, for this beautiful talk. Very interesting, illuminating. Are there any questions? Well, I have some questions. Now, you mentioned that for the anti-de Sitter case, it's not globally hyperbolic, but the theory still goes.
Mm-hmm.
About more general situations, what I have in mind is a space with manifolds, with boundaries, and not globally hyperbolic, and that I have also a quantum field on the boundary. Suppose you have, say, two parallel planes.
Yeah. So maybe let me say first the following. There's a different situation depending on the kind of a boundary.
Mm-hmm.
If you have a time-like boundary at spatial infinity, which is the case of anti-de Sitter, this is not a serious problem, because then you, if needed, you put some boundary condition.
Mm-hmm.
A more serious problem, if you have space-like boundary at a given time, so the space-time begins at a certain moment of time, and then perhaps it ends at another. Then one has to change the formalism. Then it's a different situation. So, but if these are boundary conditions at spatial infinity, you can put them, and you can in principle you can study physics on such a space-time.
Well, another question, you mentioned in case which is not asymptotically stationary, that you can define in and out vacuum. But when it is stationary asymptotically, it's clear what we mean. It's kind of a scattering situation, right?
Yes, yes, exactly.
In free and out free. But
yeah.
What do you mean physically by in and out when it's not stationary asymptotically?
Well, okay, I don't have a general answer to this. Now, in the de Sitter space, it is not asymptotically stationary, but it after taking a conformal factor, after dividing by a conformal factor, it becomes asymptotically stationary.
Okay, so in that case, you're back in.
So in some generalized sense, it still is. But it's I mean, this conformal factor is actually very big. It's exponentially growing, so it messes up things. But I mean, I don't have a general theory, but I suppose that for conformally asymptotically stationary spacetimes, you still can speak about in and out states.
And will they have the same meaning as scattering meaning that you started with?
Well, to some extent, I don't know. I mean, these questions are not posed in the literature, except in my few papers. Which so this is not what the established researchers in this subject study.
Well, that's making it even more interesting, right?
Yeah, I think so. I came quite recently to this subject, and so I'm still an outsider, and I'm asking questions which are sort of not asked by the mainstream.
Yeah. Well, okay. It's 10:05. There will be time for one more question if there is any. Well, then otherwise we thank again for your beautiful lecture, and we have some 10 minutes. We reconvene at 10:15.
See, I'm sorry, Ricardo. It's your
Yes.
call. I can't use my camera, and when I try to use it, it's written that the organizer stopped it.
The organizer stopped the camera. Let me ask the people here. Mauricio, ¿me escuchas? Maybe I should.
Sí, ¿qué pasó, doctor?
Sí, parece que el profesor Yurko tiene eliminada la cámara, que no puede usarla. Y así nos aparece acá, así que no tiene video.
¿Quién, perdón?
Yurko. Yurko es el próximo conferencista. No, Yurko.
No.
No es Yurko. No,
No.
pero Yurko quisiera tener su cámara y no la tiene. ¿Se la puedes poner?
Sí.
Oh, okay, it works.
Okay, yes. If by some reason it was disconnected, your camera.
Yeah, thank you very much.
You're most welcome.